was to look at the order of a particular ring and then to calculate the, I believe it was idempotence of this ring, or actually the units of this ring. So the ring that they were interested in was the ring of 2 by 2 matrices with elements from Z2, which seems easy at first. How do we find out how many there are? Well, we can use a tree. There's really 4 slots in a matrix, 2 by 2 matrix to fill. And you can consider each one of these branches as a slot and make a path. So you could start in the first slot with a 1. In the second slot, it branches out to be either a 1 or a 0. In the third slot, it could be 1 or a 0, 1 or a 0. So you just make the choices. And then you count the number of paths. So the first path would be a matrix filled with all 1s. Second path would be a matrix filled with all 1s and a 0 at the end, and so forth. So we get 3, 4, and then I'm going to start over because I have a symmetric set of paths here. 1, 2, 3, 4. So there's a total of 8 paths. Now realize that I could do the same exact thing with 0 in the first slot as I did with just 1 in the first slot. So if I replace that 1 with a 0, we would again get another 8 total. So the grand total would represent 16 total paths. So the order of this ring is 16. So the next part of this problem, they wanted you to list all the units. You're in luck. If they had said Z4, you would have been in a bit of trouble. But Z2 happens to be a field. And because M2 of Z2 represents linear transformations on the vector space Z2 to Z2, 2 component vectors, instead of R2 to R2, you have Z2 squared to Z2 squared, 2 component vectors to 2 component vectors. Well, all the stuff that you learned in linear algebra applies. And a matrix from linear algebra was invertible if the determinant was not 0. So the same theorem applies here. Because if you go back and look in your linear algebra book, they would have told you that everything they do would hold true as long as your vector space was defined as over a field. So this determinant is 0 if A and B are simultaneously 0, if C and D are simultaneously 0, or if everything is equal to 1. So we can rule all of them out and look at the cases where they're not equal. AD is not equal to BC. Well, they're not equal as long as A is 0, D is 1, B is 1, C is 1. And every shift of this would also apply. So not just that particular A, but 0 in one spot would make this not equality hold. Another way to get AD not equal to BC is if AD is 0 and BC is 1. Well, that can happen if A is 0, 1, 1, 0, and then you count a shift. So you just rotate all the elements. That also would cause the same problem. And that gives me a total of 6 different units. And I know I've got them all because I'm looking at the determinant equation.